Good afternoon, this is Annie Schweitzer, and quick little video here on drag and what it is. Now we're, of course, talking a lot of stuff about friction, so we're kind of looking to look at one unique type of friction called drag. So some of the ideas here we're looking at is, what is drag? What are the factors that affect drag? How do you calculate drag? And how is this going to affect eventually terminal velocity? So anytime you move through, whether it's a gas or a liquid, you're going to have some amount of drag that you're going to feel. So you could draw a picture of this as whether you're falling from the sky, could be a raindrop, for example. Raindrop is coming, it falls at a certain speed, and as it falls, it hits particles of air which slow it down. This falling actually creates this little teardrop shape. If I can draw a teardrop shape, ends up being the best shape for it to fall. Otherwise, you could be something as much as just swimming through water, and as you swim through the water provides you with drag. They are constantly in Olympic swimming trying to create new suits that minimize drag, and some of these suits have been very, very good at reducing drag. Otherwise, so drag is your resistance to movement. Let me get that out of the way here. Well. Sorry about that. To movement through a liquid, or you can be a gas, through a liquid or a gas. All right. So and I think drag essentially, it's pretty understandable. It's friction. Drag is friction. We feel it. You can stick your hand out the window. Stick your head out the window. You drive a motorcycle through air. Anytime you're encountering a moving body through a liquid, you're going to encounter some drag. So there are lots of examples of this. We have, let's say, just putting your hand outside of a window. So a car definitely feels drag, and they will. It's friction. It's resisting and moving. If you're walking through water, you can walk through water, and a stream, for example, you're gonna feel the drag of water on you. Lots and lots and lots of examples of drag. It's basically resistance of something flowing across another substance. It's a form of friction. It will resist movement. All right. So what factors affect drag? And we could just take this example and say, okay, well. Just take the whole idea of something falling from the sky, whether it be a raindrop or whether it be, there's the old adage of a penny dropped off the Empire State Building, and they always say that it would crack, cement on the bottom. Well, that could be true as long as it would reach a certain level of velocity, and who's to say that it wouldn't reach terminal velocity before it gets up to that high of a speed. It's not going to keep going faster and faster and faster. So there are some things that affect drag. So factors that affect drag. Okay, well, let's think of it. Well, one is going to be the surface area. Okay. Obviously, if you have a parachute and you're jumping out of an airplane, as that parachute opens, that maximizes your surface area and therefore increases drag. So increased surface area, increased drag. That's probably, well, I guess another one might be, let's see, your velocity. If you stick your hand out the window of your car, you're going to feel drag. The speed of your car really determines the level of drag that you feel. If you're going fast enough, it might be hard even to stick your hand out the window. But velocity, definitely, and it makes sense. You're hitting particles. As you travel through the medium, you're running into potentially stationary particles. The faster you're going, the more energy you have. The more energy you have, um, you know, the more energy can be applied to these particles, and therefore more particles that you're hitting that are resisting this motion. So velocity, definitely. It's like running through a crowd of people. The faster you run, the harder you hit them. Um, Another one might be, lots of things here. We might call this environmental factors. Okay, things like, let's say, the humidity. Let's talk more of the atmosphere. Okay, the density of the fluid, whether you're flowing through water or you're flowing through the atmosphere, and maybe even the height of the atmosphere. So it could even be, the type of fluid, type of substance, whether it be a liquid or a gas. Again, that would go directly to density. Another one might just be the surface, not the surface area, but the surface. Scientists are getting really good at creating suits that will simply, as you have a person swimming, for example, and you have water, H2O, and a person is sliding past that water, the surface upon that and how it either grips to the water particles or just slides right past them really makes a big difference. So how a surface attaches to, or how it gleams through a fluid really makes a difference as far as how well it flows, how easily it flows. You could have something like a rusty car driving down the road, or a cleanly painted car. Those two will have much different resistance factors. So the surface of an actual substance is a very big factor as to how it flows through some sort of liquid. If you're swimming and you wear a shirt versus if you wear just just either a swimsuit, or if you're no shirt at all, or just your skin. So either way, those surfaces have different factors. Next one, how do you calculate drag? All right, so in this case, this is one calculation which really you're never going to have to derive, but it is equal to the drag, which is that force of friction. This is a force of friction, so it would be measured in newtons. Again, it resists motion. So if you have no motion, you have no friction. You have no drag. We have our coefficient of friction, or this. We'll explain in a second. Is k times a times velocity squared. All right. Now, in this case, k is going to encapsulate all of the various factors. It could be the environmental factors and the surface area, these two guys right here. Sometimes they may have it as being two pieces, where we have one will represent, let's say, P might be the density, and another variable, K or C, sometimes they call it K or C, different variable names, doesn't matter, it's a variable, could represent some of the environmental factors, or some of the specific details as far as surface of the substance or whatever. So with all of these factors combined, we'll come up with essentially one variable that represents how well that particular item flows through a particular medium. Next, we have this here, which is surface area. You know very well that if you take a piece of paper and you drop it, it drops with a certain amount of surface area. If you were to crinkle that piece of paper up and drop it, it would drop completely different. That's going to change not only the coefficient of drag, which is this guy here, but also changes the surface area. And this is simply your velocity. Okay. Now, pretty simple mathematics, works quite nicely. How do I calculate it? Okay, so at this point, we just need to be given some information, given the coefficient of friction, given the area, give us the velocity, and we can very well solve for drag. How does the drag affect the terminal velocity? And I guess we should at some point discuss what is terminal velocity. What is terminal velocity? Okay. Now again, there's the old sort of idea that if you were to drop a penny off of the Empire State Building, which is a very tall building, that, let's draw that building up here, not a very good picture. That Empire State Building is located in New York City, and it has some sort of steeple on it, and it's very visible from quite a long ways. Anyways, if you could get up there and toss something off of it, let's say a penny, for example, and as it starts to travel down, we have a blow-up view of the penny, okay, and of course, if it fell straight like this, it would experience more friction than if it fell, horizontally, but we'll assume that this thing will be topping and turning, so its surface area will change slightly as it turns and tips. But as it falls, it's going to travel faster and faster and faster, and without air resistance, this particular penny would just continue accelerating at the rate of gravity, which is 9.8 meters per second squared. And we could easily calculate out the height of, we could go online and find the height of the Empire State Building, and based on that height, you could figure out how fast it would be going when it hit the bottom. But in this case, we have the penny, and it's going to start hitting the atmosphere. Now, at very slow speeds, okay, there is a very, because the velocity is small, there's very little drag, almost none. So the drag is equal to the coefficient of friction times the area times the velocity squared. If this is very, very near zero, then my drag is next to nothing, and this thing will essentially, the penny will essentially start to fall at an acceleration rate of 9.8 meters per second squared. The vector at this point would represent the force of gravity. The force of gravity equals the mass of the item times the acceleration of the gravity, which is that of gravity, 9.8 meters per second. But as it gets going faster and faster and faster, we start to get a resistive force going in the other direction. And that is the resistance of drag. So in this case, as the velocity picks up faster and faster and faster, the force of gravity will always be the same. So on my penny, I have the force of gravity will not change. Force of gravity equals the mass of the item times the acceleration due to gravity. But as it gets faster and faster and faster, the friction starts building and building, and eventually we get to a point where the force of drag equals essentially the weight of this thing. Force of gravity times the mass, which we often think of as being the weight. So that's kind of unique that we think that, okay, my force of drag, in order to stop the acceleration, will just have to be equal to the weight. Now again, is the object actually stopping? No, it's just stopping the acceleration. So if I drew my picture out again, I would have balanced forces, the force of my weight going down and the force of friction going up, in this case drag. And if these two are equal, we're either one of two things are happening. Either we are stationary, zero velocity, or we are simply moving at a constant speed, which is what we are doing in this case. So at some point, this thing will start falling, falling, falling until drag equals the weight. Okay. Now, in this case, we could solve it out. If the drag equals the coefficient of drag times the area times velocity squared equals the weight, which is the force times the mass, force of gravity times the mass, which equals the weight. So these two things are in fact equal. Then we can say that these two things are equal as well. Let's solve for velocity, and velocity equals, divide out the force of gravity times the mass. Underneath here is going to be the coefficient of friction and the area, and we'll square root that to get the velocity all by itself. And this is our wonderful equation for the terminal velocity. Okay. Now again, you might see it look a little different. And the only way you'd see it different is if they take the K and they changed it into maybe a couple different pieces to account for a few of the different variables that might be involved in this particular item. But that essentially is terminal velocity. What do I really want to know when I'm looking at terminal velocity? All right. First of all, what is drag? So what is it? What is the factor that affect drag? Calculation, that's just a plug and chug idea. But more importantly, how does it affect terminal velocity? And can you draw a picture out showing sort of how drag and your weight balance each other? All right. Quick introduction into drag and terminal velocity.